Alright everyone, welcome back to my Vpython tutorial video 2. So we already covered how to work with just some of the basic stuff in Python. The last video is not supposed to be a very in-depth tutorial on Python. Hopefully you'll pick up a lot of those skills as we continue working, but they're at least an introduction so you've seen them before. And now I want to show you guys what you get when you add Vpython, when you add this package to it. So I just created a bunch of stuff. As a note, if you want help on any of your Vpython, you can literally just type in like Vpython onto Google and look right here. There's a vpython.org, and this is actually made by the author of the textbook to have all of this information for you. So particularly they have examples of stuff worked out. The documentation area is where I always point people to, and this has all the information you need to work with any of the stuff here. So for example, we're going to be learning how to create objects. So they're arrows, boxes, you can do cones, helix, all this stuff. Today in this video, I'm going to show you guys how to work with arrows, boxes, and spheres. And then you guys can feel free to look at the rest if you really want. There's also a bunch of other things, like if you're working with 3D objects, we're going to learn how to do to give objects color in this video. So for example, this has a whole thing, all the information you could possibly need about color in Vpython. So definitely feel free to check those out. All the information I'm gonna say here is on this website. I'm just gonna work through some examples and stuff. And also I want to talk about vectors, because vectors are a huge convenience when you're looking at Python. So we're gonna start right here, and I'm just going to go through here. So I have a few examples. So basically, as you can see, I've got some stuff ironed out. A vector is essentially just a collection of 3 points. So it is 3 numbers, x, y, and z respectively. So x, y, z. And that is just going to be this useful 3D object. So we use this in plenty of points in Vpython. The most important one is probably position, or that's the most common one we use it for. But honestly, like, you can just have a vector just to do math with in the background. And let me tell you, you guys are getting spoiled in Vpython by having all of this done for you. There are programs that I've written where I've had to manually create some of the math functions that Vpython just has built in, and it's actually very intuitive the way Vpython does it. So I'm going to go through just some of those so you know vaguely how to work with these vector objects. But what I'm going to do first is just see that you can name a vector. So in the same way you would name like just a number, you can name a vector object. And so you always say that by saying vec, or you can spell out the whole vector. Either way is fine. I like vec just because it's shorter. And then you give it your x, y, and z coordinates. So if I just print this vector, notice it's just going to print out the x, y, z coordinates of it. Alright, so I'm going to show you that Vpython does some math for you. So I'm going to have a vector that is just the unit vector in the x direction, and then b here is the unit vector in the y direction, and I'm going to add them together to create a new vector c. So typically, you expect this to work just like any vector math. So the resulting vector we expect to be 1, 1, 0. So if I print c, you can see we get 1, 1, 0 out, which is super nice. Again, this may seem simple, but this is actually not something that is in normal Python, and they had to build this in, and it's actually very well done. So now I'm going to talk about, so I'm just going to get a vector 1, 2, 3, so x is equal 1, y is equal to 2, z equals 3, and I'm going to show that you can also just scale it. So you can do 5 times that, or some scalar value times your vector, and it will just scale it the same way you expect scalar multiplication to work for vectors. So if I just print out 5 times this vector, notice it's 5, 10, 15 rather than 1, 2, 3. Next, I'm going to show you, and these are probably the best parts about this, is there's a dot product and cross product function. If you haven't gotten to this yet in your class, what you will realize is these are really annoying to calculate by hand. And sometimes, honestly, if I have a problem that I want to do really quickly, sometimes I'll just load up a Vpython script and get it to do the dot and cross products for me, because this will do all the math involved. If you are familiar with these, you know how annoying particularly the cross product can be. But like I created 2 vectors, so you can see just any 2 vectors here. And if you want a dot product between them, there's actually a couple ways to do this in Vpython. This is the way I like to do it. So, you know, I'm just saying like a dot b equals, and then you can say a period dot, and then b. So basically, the way this is working, and this is like probably way too much information for you, is a is something that we call an object in Python. And when you put like this period, you're getting a function out of that object. So one of the functions built into the vector object is the dot function. And dotting, you feed it another variable if it needs one, and then it will output some value, some return. So here I'm saying a dot b, and that will put out the dot product. And if you guys are unaware with how dot product works, this will output a scalar. And then you can also do the same thing with cross product, a cross b, and this will output a vector for you that's perpendicular to both a and b. And if I just show you, like, it's printing out, it's a scalar value. If you sit down and do the math by hand, you will get 31 for the dot product of those two vectors. And if you sit down and do the math by hand, you will get this vector for the cross product. So that saves you so much time. You guys do not even know how annoying that is to not have that functionality built in. So it's so great that it's built in here. So the last thing I want to show you is there's also internal math that the vectors have within itself. So if I'm just showing you here, I've created some vector. This is remember this is a 3, 4, 0. So this is going to form a 3, 4, 5 triangle. If you guys are not familiar, it's just a common triangle because one leg of it is 3, one leg is 4. So the magnitude of this vector you expect to be 5. And you can actually just tell it to give you the magnitude of a vector. So I have here just like magnitude of a equals, and then a dot mag. And again, magnitude is just a function it has built into this object. So you just say a dot mag, and it will do it all for you. And then you can also get the hat form of a vector. So a hat equals a dot hat. And so this is super useful because I see a lot of time people will be doing vectors and they will calculate this by hand. So if they have a vector r and you want the hat vector, usually you have to take the magnitude. So they will literally dot r with itself and take the square root to get the magnitude. And then after they have the magnitude, you got to divide the vector by that magnitude. And that's so much more complicated than just saying dot hat. Utilize these cool functions that are so useful to you. So if I just print this out, notice that the output is 5. And the hat form of that, if you go through the math, you will find that the vector divided by 5 is 0.6, comma 0.8, comma 0. So super useful. That vector math is just so nice to have. Now vectors we're going to use a lot in our object creation. So I'm going to immediately go into that, and we're going to start off by looking at spheres. So right here, so this is a program I wrote. Don't worry about this code right yet. I just want to have that ready. But pretty much all these objects you could go through for Python. First of all, I'll just show you particularly the sphere object in Vpython. So this has like some of the basic documentation have a sphere. But if you want to create a sphere, you just say sphere, open parentheses, and then close parentheses. And you can put information about the sphere on the inside. So I'm just going to create a default sphere, right? So this is just a default. The defaults for a lot of these objects are listed on vpython.org, particularly for the sphere object. Its location is at the origin, its color is white, its radius is 1, things like that. Those are all attributes you can choose to change, but it has just a default thing to it. So a lot of these, if you don't specify something, it will just use the default value. But yeah, so I'm going to leave that sphere in the program just so you can see where we're creating other stuff. So I'm going to create another sphere. So I'm going to just show you some of the attributes you can add to a sphere. And one of the first things I always look at is position. So for example, I can say POS, and POS is the position. You can either write out POS or the full word position. And what POS is expecting is a vector. So if you give it anything that's not a vector, it's going to complain. Just as a note, so we need to say this vec, open parentheses, close parentheses, and we need to give it an x, y, and z coordinate. So I'm going to place this. I don't want to place it at the origin so we can see it's different than the other sphere. So I'm going to place this, I don't know, I'm going to put it at 3, 3, 0. So notice the x is 3, the y is 3, so I expect to be placing it to the right and upwards. and it's still in the z-plane. So if I run this, notice this is our original sphere, and this is the sphere that's at 3, 3. That's cool. Another thing you can do is affect the radius of the sphere. So so if you want to affect the radius, you just type in radius, and it's expecting some number, either an integer or float or something like that. So it's not expecting a vector, for example. So if you do give it a vector, it's going to crash. And this is just how big you want the radius of the sphere to be. So for example, this sphere winds up being one, so just units. You have to kind of pick your own units in this, so you just have to choose to be consistent. So if you want it to be, quote unquote meters, you can be. You just need to be consistent about your units. But basically, this guy's radius defaults to be 1, so I'm just going to give it like 0.25. I'm going to make it a quarter the radius. And if I run this program, notice that it is now much smaller, so I can kind of play around with that. I can make it 1/2 if I want, and adjust the size accordingly, and all of that is taken care of. And then another really big thing is you can affect the color. So color is expecting a vector. Basically, how color works is, as you can imagine, it's just going to change the color of the object. And it's expecting a vector, and the x, y, and z components of the vector are going to be red, green, and blue. So how much red, how much green, and how much blue is in it. So if I say 1, 0, 0, it has a lot of red, no green, and no blue. So you expect this sphere to be red. And notice that it is red. These numbers can go up pretty high. Like, I'm pretty sure this is an acceptable value. And notice that it's like just very brightly red now. Typically, I like to keep the values of the color functions between 0 and 1. I find that it's not very useful to go super high on them, but that is an option if you so care. And then notice that, so if I want to get purple, so I want a bunch of red and a bunch of blue, so I'm going to make the z component also 1. So this is a lot of red, no green, and a lot of blue. And notice that now the sphere is purple, which is cool. There's also some pre-programmed colors in there. So I'm going to go here to the color thing. And you can notice that they give some pre-programmed in colors, and they tell you what that vector would be. And this is the Python language for that color. So for example, let's say I want mine to be orange. I can literally just type in color.orange. And now if I run this code, it will automatically pull the vector that would correlate to the orange color and print it out here on the screen, which is super nice for you. So you have all this stuff, and you can pull out these individual values. So obviously there's a lot more that you can go through. I think the last one I'll kind of go through is like opacity. And opacity is just literally how opaque it is. So I can set this to like 0.1, and you're barely going to be able to see this sphere up to the right. It's just very opaque, a lot of light's going through it, and you can kind of see through it. So that's sort of useful if you, particularly I find it useful when I'm projecting stuff and I want things to line up in very particular positions. I will just create like an opaque box or something and use that to help line up where I want objects to be located, just for visual aesthetic reasons, right? So yeah, that's pretty much all of the sphere stuff. I'm just gonna comment that out, and I'm gonna go down here to another last thing I wanted to talk about. So all of these objects, you can also choose to name them. So up here, I didn't name the object. You don't have to name it. But if you so choose, you can name an object, and you can give it any name. So here I'm just calling it A. And what you can do with this is later on, if you want certain information about the sphere, so if you either want to get that information out or you want to change it, so if you want to change some attribute about the sphere, like you want to change its color, you can go back and you can just say the name of that sphere, dot, and then the property that is associated to. So a.pos is just the vector that correlates to the position. And let's say I want to change it. So here I'm creating a sphere, and its default is to be at the origin, and I'm moving it to be at the value 10, 0, 0. I'm also giving it a new color. So this would just be like a kind of lightish gray. And then I'm changing the radius to be a little bit smaller. So if I run this, notice that there's a lightish gray sphere out about 10 units away from the origin, and it's a little smaller than our first one. So you can change things after you create an object, And that's going to be very useful when we do simulations later, because when we want objects to be moving, obviously it's useful to create the sphere in one particular location and then change the position later on as we want it to move somewhere else. So when you start making these cool movies and stuff, that's some of the really interesting stuff. So just I'll actually show you just a cool example. So I think I have a I have a model of the solar system running here. So these are just a bunch of spheres, and I have them moving and changing their positions in time, so you can see stuff. I also have a certain attribute called make trail set to true, so that these guys are creating a trail as they travel around. But here I have the Sun, Mercury, Venus, Earth, and Mars, and I'm going to go down to, they also have this make trail, and you can set this either to true or false. I wanted there to be some kind of global path variable, so I just named path and I set it equal to true. But essentially, you would do this and set it equal to true if you want it to be a true color. Notice I also programmed in like a bunch of other planets: Jupiter, Saturn, Uranus, and Neptune. But yeah, essentially, like you can see, this is where we're trying to go with this object creation. And notice that like being able to change the colors helps you tell like which is which. I have all the correct radii for these planets scaled up, I think. So these are like relative to each other, correctly sized. Just a bunch of really cool stuff like that. Aside from the Sun. The Sun's really small in this program, but that's where we're trying to go with that, and that's some of the cool stuff you can do with spheres. So you can also do very similar stuff with arrows. So that's the next thing I kind of wanted to get at. And I don't actually have anything ready here in this program because I figured I would just show you. Once you've created one of these objects, it turns out they share a lot of the same properties. But if you just create an arrow, it's going to create a white arrow that is 1 unit long pointing straight to the right. So I'm going to create another arrow. And this is going to be the one where I'll just show you some of the cool properties. So I can set its position, and let's say I just want it to be above where the first arrow is. So I'm going to set its position to be the vector 0, 4, 0. So now it's going to create a second arrow above the first one. Yep, up here. And this is about 4 units away. I want to make a note that the position of the arrow is where the base of the tail is. Like in the sphere object, the position was the center of the sphere. But for us, this arrow is going to be at the very base, so where this ends. And then we're going to talk about something later, the axis, and the axis tells you how it points. But let's get into that, because the next thing I like to cover with arrows, and this is pretty much the main difference from spheres, which is the axis of the arrow is very commonly used. Spheres do have an axis property, but you don't usually use them too much unless you're just really a stickler about the way like light's shining on your sphere. But essentially, axis tells you the vector as where it points and how long it points. So I can set this vector to anything I want. So the default vector is 1, 0, 0. That is the vector that points 1 unit to the right. So let's say I just want to make this point down and to the right. So to the right would be some positive number. So I'm just going to say 3. I want it to be pointing downwards. Let's say -2 and 0. And if I run this program, notice the arrow got bigger and it's pointing down to the right. And let's say like I don't like the fact that it got bigger, so I want to change this property called the shaft width. Shaft width. And this is just expecting some number, and that's going to tell you how wide the shaft is. So if I just set this to 0.1. Sorry, shaft width is one word. If I set this to 0.1, notice that the shaft is now back to being small again, and you could play around with that. So that's just like a convenience of being able to play with these. Again, it's a nice aesthetic tool that you can use. These guys also have color, so color is equal to color.cyan. Like that's a color that's programmed in here, and now it's cyan colored. Yeah, so all that is super useful. You can do the same thing. You can name arrows so that you can get them to point in different directions later. A bunch of cool stuff like that. Again, once you've worked with one of these objects, you kind of have an idea of how to work with all of them. So let's go back to our stuff here, and I'm also going to just look at this box thing. So box is another object, and it just creates a rectangular prism of certain dimensions and things like that. So default box has dimensions 1, 1, and 1. So the X, Y, and Z direction all are 1 long, and its location is the origin. Again, like the sphere, the position of the box is the center of the box. So let's just for comparison, I'm going to create a box. I'm going to just create a box, and its position is going to be some vector, and let's put it at 3, 4, 0. Again, just along that 3, 4 triangle. So I've created a box up and to the right. I can change color equals color dot red, and now it's a red box. One of the biggest things about box that's different from the other two, it also has an axis property. So let's just give it an axis, and I'm going to give it the vector 1, 1, 0, and that's just going to change the way the box is pointing. So notice that it's pointing up and to the right. And it will also accept a size value. So I'm just going to say size. And size is expecting a vector. And for the size vector, you can feed it how far it should be stretched in the x, y, and z directions. So let's say I'm going to remove this axis thing just so it's very obvious the way that we're creating this size. But let's say I want it to be really long in the x. So let's say I want it to be like too long in the x. I want it to be a little narrower in the y, so I'm going to be half as y. I want it to look kind of like a pancake in the z direction, so really, really tiny. It's 0.05. And if I run this, notice that it's longer in the x, less long in the y, and it's kind of like that pancake thick consistency. And then notice that, again, it's still located, the center of this box is about right here. And so if this box is too long in the x, then from the center, it's 1 unit there and then 1 unit there. So just that's something to be aware of when you're messing with boxes. If you don't like the size vector, you can just change like the length. And I can set this to 0.4 or something crazy like that. And notice that the length winds up being for the x direction. There's also width and height that you can change. So again, I don't want to spend too much time on this, but I'll change the width and height. I'm going to set this equal to 3. And so notice that I made it taller and thinner. So this was the width and this is the height. But that's pretty much all the box properties. And again, you can name them and get out properties about this later. I like to just work with the size vector, but you can work with these length, width, height if you really care. And all of that's super nice. And then the last thing I want to get to before we start doing some examples is I want to do graphs. So graphs are going to be very useful for visualizing some of your data. So I'm just going to show you because I already created something, but essentially what you do is you create a graph, and this is a collection of curves, right? So they have this thing called a G-curve, which is a line that represents a collection of data points. So as your simulations usually go, you will be getting data points, and you will be adding them to this thing that we call a G-curve. And the main property I usually give my G-curves is a color. There's obviously other properties, and there are properties that you can give graphs. Again, you should go into the working with Vpython section and look at graphs. Like, you can do cool stuff, like get them to be looking like this, where there's area underneath filled or dotted. There's a bunch of cool stuff, but you just need to read through all of the information out here about graphs. I'm just giving you the very basics you need to work through the class, and then maybe we'll look at those later on. But essentially, if I create, I'll get to what this graph does later, but essentially you create a G-curve, and I'm just going to say I want it to print out colors, points in the color red. And then I have the value x at -10, and I'm going to say while x is less than or equal to 10, so x is going to go at -10, and it's going to eventually be equal to 10. Then every 30, or I'm going to set this to 50 just so it plots quickly. I'm going to plot a point. So you take the name of your G-curve, and this is why I named it, is so later I can say dot plot, and I can plot the x component of the graph and the y component of the graph. So for here, I'm just plotting the function x squared. So I'm plotting x and then x squared in the y, and then I'm going to increase x by 0.1 just to give it a smooth looking function. But notice that it's starting at -10, and then it's going and it's slowly plotting up here. Obviously, if I didn't have this rate at all, it would just immediately plot all these points for me. So typically how I use these are during the middle of a simulation. I will be running this, so it'll plot as you go in the simulation. So this is kind of typically what you should get used to seeing. You can get this to be very specified dimensions. So this thing kind of just automatically chose, positive 120, 0, negative 10 to 10, based on how I plotted things. But you can kind of get it to go anywhere. And I also want to note, this is how you square things in Python. It's asterisk, asterisk, and then after that it's the number is what you're raising it to the power of. I could also have just said x times x. So I kind of want to show you now what this graph does, and for that I'm going to create another value. I'm going to create x cubed. So we're going to do literally the same thing, and I'm going to name another G curve, and let's say I want it to plot in blue, so color dot blue, right? So now in here, if I want to plot points, I already have it going from negative 10 to 10. Sorry, forgive my dog, he's sniffing in the background. Then I'm going to take the name of our plot, x cubed, and I'm going to plot an x and y point. So I'm going to right here plot x comma x cubed, right? So what you should see is both of these are on the same curve. So this guy's starting at negative 1,000, and then it's going up to positive 1,000 because that's what 10 cubes or negative 10 cubed and 10 cubed are. Notice, however, though, that this plot now is like, it just kind of looks bad because the x squared plot has lost a lot of its functionality. Sometimes you want things to be plotted on the same graph, but sometimes you want to create two separate graphs. And for that, pretty much everything under this, where I created this graph, that is going to have these curves under it. So if I want to create another one, I'll just create another curve. So I'll just create display 2, and it's going to be another graph. And what this is going to do is it's going to create a separate white sheet where I can be plotting points. So now x squared is going to be plotted, and then x cubed is going to be plotted on a different graph. So you can see there, I have x cubed down here and x squared up here, and they're on these nice separate curves, and everyone is happy. So that's kind of like a fine point that's hard to really get at in some of these, but I think that it's super useful. So I know that we've been going pretty long, but I now want to get into some examples. So I have two examples. One of them's already coded just to show you, and another one I wanted to go through an actual problem from the book. So problem 69 here, if I run it, basically what this problem asks you to do is it asks you to create a bunch of spheres, and it wants them to be at the corners of a box that is 6 by 6 by 6. And it wants an arrow pointing from one corner to an opposite diagonal corner. And then notice that it also asks these to be different colored spheres. So this is just a good, like, encompassing example of everything that we covered in this. So let's go, and we're actually going to create a new problem. What was it? 66? P69. All right. So we're going to get started with this. Now, the first thing that I recommend is usually people draw this out. Because I'm working on the computer here and I can't really show you what I'm drawing. I think another great way to project this is we want to be creating these spheres first, just because that's kind of the most convenient place to put them. And so I'm going to try and figure out where I want to put the spheres. And we want to place them at the corners of this 6 by 6 by 6 box. So what I would recommend first is we just create a box. And I'm going to, make its size. It's already located at the origin. Size is equal to the vector 6, 6, 6. And I'm also going to change the opacity to 0.2. Just something like that. And what I'm doing here is I'm just creating this kind of thing that we can look through, this very translucent box, and that's going to be useful. And then at the end of the program, we're going to delete the box because that's not actually part of it. But it's just going to be a useful visualization tool so you can see where this stuff is happening. So remember, this box is at the origin. And so what I want to do at first is I want to figure out where is this point, right? So if this is the origin, what is the x distance from the origin to this x side wall here? Well, as I said before, because this is 6 by 6 by 6, if I want just half that distance, this is obviously 3 units. So x is going to be 3 for wherever we're placing spheres that are along this side of the box. And then if I want to go up another 3 units, I can get to one of these 2 points. And then obviously if I go forward 3 in the z, I can get to this exact point here. So that's exactly what I'm going to do. So now I'm just going to create a sphere, and its position is going to be the vector 3, 3, 3. And if I place this, notice that this sphere is exactly on that corner. So now I'm going to give it a color just to go ahead and have that color attribute reminded. And notice that now I can see through this box and kind of see where all these spheres and stuff are going on. And we'll just do a few things. I also want the radius. Radius is equal to a number. And I'm going to set this equal to 0.5. I just like it to be a little smaller because it'll look a little nicer. And I typoed radius. But notice that it's just a bit of a smaller sphere now. So that's kind of cool. And now you just go about and try and figure out where the next point. So this point is obviously 3, 3, negative 3, right? And this is 3, negative 3, 3, 3, negative 3, negative 3. Notice that there are 8 total combinations that you can do with this positive and negative, and there are 8 corners of the box. So what I would do is I would just copy and paste 8 total box spheres. So 1, 2, 3, 4, 5, 6, 7, 8. There's also something called copy in Vpython. I wanted to clone. So you can also just clone things. So if you create a box, for example, in this situation, and you named it, you could just say the name of that and .clone, and it would create a new box. And if you gave it any new properties, it would just change those properties about it. So it would maintain the rest of the properties and just change these. So that cloning is also something you can do. Cloning is probably something that I would find useful in a while loop if you just wanted to reduce the amount of code. But honestly, I like not using clone right here because I think it's just simpler for students to understand. If you never know how to use clone, I don't think you will be significantly hampered in this class. But for now, we just want to get every possible combination of plus and minus 3 for this x, y, and z. And I kind of do stuff like this a lot. So I already know where all of these should go. But notice that I've created every possible combination. So none of these are the same, and this is everything you can do. And notice that they are located at the corners of this cube, right? So that's cool. So now I'm just gonna hashtag out our box, comment it out, and now we just have all of our cubes located right here at the corners, which is really nice. And again, I want to make them slightly different colors. So I'm gonna make like this guy blue, and this guy green, and maybe yellow. And I'll leave that guy red. I'll do another blue, another green, and another yellow. So now if I run this, all of a sudden we have all of our different colors, which is cool. Again, like it doesn't specify which colors need to be where, so I'm just kind of vaguely placing them wherever I want. They all have the same radius. And now what we want is we want an arrow pointing from one of these corners to the opposite corner. So maybe this guy to this guy, or this guy to this guy. Personally, because that guy is located at -3, -3, -3, and this guy is located at 3, 3, 3, I find it easier to go here to here, but you can do this in any order. You could even start here and go there. So I'm going to create an arrow. So, oh my god, sorry. I'm missing all my clicks right now. So I'm just going to create an arrow object, and notice that it's just going to be pointing straight to the right. I haven't given it any properties yet. And the first things first is we want this arrow to be starting at this base sphere here. And recall that the position thing of the arrow is the tail end of the arrow. So if I want to start here, I need to move the position to that guy's position. So I'm going to show you something cool here because I like this. So I'm going to actually name these two spheres that I care about, A and B. And this is where naming spheres becomes useful. So notice that nothing has changed about the program. Naming them doesn't change the way the code executes, really. But now, if I want to move the arrow's position, I can just set the arrow's position equal to B's position. So B.pos represents the position component of the B object, whatever that winds up being. In this case, it's the sphere. So if I want to get that guy's position, I can just set it equal to I can set the arrow's position equal to that guy's position, and all of a sudden the arrow has now been moved down to this guy, right? And now I can give this arrow a vector. So you could just give it axis equals vector, and remember, axis is going to tell you where the arrow points. And now because it's starting at -3, -3, -3, and it wants to go up to 3, 3, 3, notice that if I set this to 3, 3, 3, it's not actually going to reach all the way to that sphere. That's because the distance between this guy in the x direction is not 3, it's 6. It's -3 to +3, so you need to add 6 to that. So, and it's the same thing for y and z. So I need to set this to 6, 6, 6. And notice that this arrow points over. I think that's kind of a fat arrow, so let's just change the shaft width equal to 0.2. How's that look? That looks kind of skinny. So I mean, notice that like if you run the code and you don't like the way it looks, you can always just change the way it looks after the execution of the code, and you can play around with things. There's no really correct thing. You don't have to change the shaft width at all for this problem. I just think that it's kind of nice. So I think this looks good, you know, to me. You could give the arrow a color, but I want to make a note about the axis, which is now because I've named A and B, if I want it to start at B and end at A, the typical way we do this for an arrow that starts at B and ends at A is it's A minus B. So if I take the position of A.pos, and I subtract out B.pos, that is the vector 3, 3, 3 minus -3, -3, -3, which is the vector 6, 6, 6. Right? So in general, I can do this, and if I run this program, notice the arrow is still starting here, ending here. So that's just a super useful way. If I changed which spheres were named A and B, so let's change like that guy and maybe, I don't know, that guy. Notice that the arrow is now going to be pointing. Because I coded it to start at a certain sphere's position, and I coded it to point from that sphere to a different sphere. Notice that it just automatically adjusts for me, and I don't need to think of anything at all. So it's super nice. That's where this whole naming thing and everything becomes very powerful. So yeah, that's super cool, and that's pretty much everything you need to know. This folder, I need to set this to a public folder. Actually, I need to set, yeah, this is public. This folder is going to be in the description, so feel free to go check out all of this stuff. Play with them. If you see some code that you want to change around and play with, just copy and paste it into your own version of GlowScript, and you can start playing around. But hopefully all of that was useful to you. In the next video, we'll finally get into the cool stuff, which is actually making like adding physics to all of this. So hopefully you understand vaguely how we're creating objects and how we're, you know, moving them and stuff like that, and just some of the properties. If this is overwhelming, it just takes a lot of time. Programming is one of the things that you don't learn just by watching a video. You learn it by watching and then practicing what you see. So again, you know, don't get too sidetracked. But I hope you guys learned something, and I'll see you in another video.